Okay, well, we'll get started then. Today we're going to cover a few different things, and so I just kind of want to give a little context to what we have learned as far as statistical inference has gone so far. Okay, so for statistical inference, we've learned a few methods. Okay, we have confidence intervals, for mu, and also confidence interval for mu1 minus mu2. So we have confidence intervals for a population mean and also the difference between population means. Okay, we've covered a t-test to compare independent samples, or to compare the means from independent samples. Okay. We also have, we've also covered a t-test to test, I guess, compare paired data. Okay, so we have we've covered these so far, and today we're going to add to this. We will have the Wilcoxon Mann-Whitney test, and we will also have the chi-squared test. Okay, and there's two chi-squared test. There's the goodness of fit, and then there's the chi-squared test for independence. Okay, and so maybe I will draw a line here. Okay, and so all of these methods up here, these are all for numeric variables. Okay, the confidence interval for mu and mu1 minus mu2, and to compare the means, and t-test for paired data, and the Wilcoxon Mann-Whitney test. This is all for numeric variables. Okay, the chi-squared tests will be for categorical data, or categorical variables. Okay, and this Wilcoxon Mann-Whitney test, I'm going to put a little star next to it, and this is going to be called a non-parametric test, and I'll explain what I mean by that. Okay. All right, and so this is so today we're going to cover the Wilcoxon Mann-Whitney test, which kind of will be the last of these numeric variable tests. Then we're going to learn these chi-squared tests. Okay, and then in the following weeks, so next week, we will learn ANOVA, and then the week after will be correlation and linear regression. So today's week 8, I guess. So next week, which will be 9th week, 10th week. 11th week will be, week 11 will be review. And then week 12 will be the final exam. Okay, and that will be the end of the course. So I hope you've enjoyed it. I always enjoy teaching this class, and you guys are really great students. So it's been a pleasure to teach you guys. So anyway, all right. Well, let's talk about the Wilcoxon Mann-Whitney test and then non-parametric tests as a little bit more broadly. Okay. Okay. So let me first start off by talking about what a non-parametric test is versus maybe I should start talking about parametric tests. Okay. So the t-test, whether it's for independent samples and the t-test for paired data, also and even confidence intervals that use the t-distribution. Okay, these all fall under the category of parametric tests. Okay, so these are parametric tests. Okay, and what we parametric here means involving a parameter. Do you guys remember what a parameter is? It's something that describes the population. It's a value that describes the population. Okay, so involving a parameter, and this being a value that describes or defines the population. Okay, so as far as t-tests go, that parameter that we're talking about is the population mean mu. Okay, so for t-tests, okay, so they are parametric tests, and specifically because it's about mu, they depend on the central limit theorem. Okay, so these tests, the t-test, at the heart, they work because we assume that the central limit theorem applies. Okay, and generally the central limit theorem, we can say it applies when those conditions are met. Right, so we have. Do you guys remember those conditions for using the central limit theorem? Okay. Well, so all right. So we'll back up here. Okay. So yes, we'll.
N is large enough.
Yeah, n needs to be large enough, and okay. So let's talk here. Okay. So the mean is mu. Okay, and you know the t-test. And as well as confidence intervals depend on the central limit theorem. Okay, and a lot of times we say, and basically the central limit theorem at its heart says that y bar, the sampling distribution of y bar, follows a normal distribution. Normal distribution. Okay, or a t-distribution, which is just like a, quote, relaxed version of the normal distribution, okay? But, there are a few conditions. And the conditions are the sample must be random, and independent, the values within the sample, okay? The sample must be large enough, but not too large. Okay, and then also sample must not be too large. Okay, and then this large enough condition, this is usually the hard one, okay? So what large enough means is that if the population is normal, any size sample is big enough, any size is okay, and if the population is not normal, usually 25 or more is big enough. Okay, and we said if it's really skewed or really not normal, then 25 might not be big enough, and perhaps you need to apply some kind of transformation like a log transform or a square root transform or something like that, okay? I'm hoping this is kind of feels review-ish and has been familiar. Okay, so so the problems we've encountered, generally we've said like we're going to assume the population is normal or nearly normal or something like that so that we can get away with having small samples or something, okay? But what do we do if these conditions aren't met? Okay, and so sometimes when we do our data analysis, our sample is not large enough. Okay, so sometimes we'll run into problems with this condition. Okay, and in that case, the central limit theorem may no longer be true. Okay, and so to deal with this, there's a whole subfield of statistics called nonparametric statistics, which tries to see how we can analyze data without putting these kinds of assumptions on the populations and stuff like that, okay? So nonparametric statistics okay, so these tests do not put assumptions on the population. Okay, and they generally don't involve the use of parameters. Okay, so so these tests are not, well, I'll say generally do not involve the use of parameters, okay? And so, yeah, you could take an entire course called Nonparametric Statistics, and it could be useful depending on the type of data that you encounter. In this class, we're going to learn one test, the Wilcoxon Mann-Whitney Test. We'll spend maybe 30-45 minutes, and that's going to be your full exposure to this whole field of nonparametric statistics. But basically, I'm just saying, if you're dealing with strange data where you're as you learn these other tests, you realize, well, maybe I can't make these assumptions, then perhaps nonparametric statistics is a reasonable approach. But to be honest, I don't know. It's not that popular. Okay. Okay, but it does exist. All right. Okay, so we are going to learn the Wilcoxon Mann-Whitney test. Sometimes this is just called the Mann-Whitney test. A lot of other textbooks will teach the Wilcoxon rank sum test, okay, and they are equivalent. They are not, the process is different. Okay, but essentially the conclusions of the Wilcoxon Mann-Whitney test will be equivalent to the conclusions of the Wilcoxon rank sum test in a similar way that confidence intervals for mu1 minus mu2 will produce kind of the similar conclusion as a t-test for two independent samples, and in a similar way that they come to arrive to the same conclusion. These tests they appear different, but the math that underlies them is essentially the same. Okay, and so with the Wilcoxon Mann-Whitney test, it can technically be used anytime you have two independent samples. Okay, so can be used whenever you have two independent samples with a numeric variable. So basically, any situation that you would use a t-test for independent samples, if you can use a t-test for independent samples on it, you can also use the Wilcoxon Mann-Whitney test. Okay, but in general, the Wilcoxon Mann-Whitney test, or in general, nonparametric tests, are less powerful than their parametric counterparts. And what I don't think I taught the concept of power yet, right? No. Okay. So, but I did teach type 2 error, right? Okay. Yeah, beta. Okay. So what is type 2 error?
False negative.
Yeah, false negative. Okay. It means you didn't reject the null when you should. Okay. And basically, nonparametric tests will have larger beta than their parametric counterparts. Okay. You're less likely to reject the null. It requires more data for a nonparametric test to come to a conclusion that we should reject the null hypothesis. Okay, but in a situation where it is inappropriate to use a parametric test, then you should use the nonparametric test. But okay. So anyway, Wilcoxon Mann-Whitney test can be used whenever you have the two independent samples with numeric variables. Okay, so this is less powerful than the t-test for independent samples. Okay, so we'll say Wilcoxon Mann-Whitney test has a higher beta. Okay, meaning the false negative rate is higher for the Wilcoxon Mann-Whitney test. Okay, so when do we want to use it? Okay, so we would use the Wilcoxon Mann-Whitney test basically when we can't use the t-test for independent samples. So we would use Wilcoxon Mann-Whitney test. Generally, the scenario is you have a small sample, small sample size, and then outliers are present in your data, which indicates the population is not normally distributed, okay? Okay, so this is when we would use the Wilcoxon Mann-Whitney test. Basically, because to use the t-test for independent samples, it has to be a random sample, and the sample needs to be large enough. And then if you have a small sample, then for the t-test to work, a small sample is okay as long as the population is normal. But if you have a small sample and you've got outliers in that thing, then that's an indication that the population is not normal, and then now the central limit theorem doesn't work. Okay, and so using the t-test here could be a bad move because the central limit theorem might not hold, and the t-test depends on that kind of mathematical foundation here. Okay, so this is when we would want to use the Wilcoxon Mann-Whitney test. Okay, so let's talk about how this works. So with the Wilcoxon Mann-Whitney test, the hypotheses will not use doesn't use mu, okay? It doesn't use any kind of parameters or things like that. And so it's a rather verbose hypothesis, okay? But basically, the null hypothesis will be that the distribution of the population for sample 1 is the same as the distribution of the population for sample 2. Okay, so again, here we've taken two samples, each from their own populations, and we're trying to make conclusions about the populations despite only observing two samples. Okay, and so the null hypothesis is basically the two parent populations have the same distribution. Okay, that's basically it. And then the alternative would be that one of the population distributions produces larger values or smaller values than the other one. Okay, so we'll say one of the populations tends to produce larger values than the other population. Okay, and if I just leave it like this would be a non-directional alternative. If I specify population A tends to produce larger values than population B, then that would be a directional one. Or if I say population B tends to produce larger values than population A, that would also be directional. But if I just say one of the populations produces values different from the other one or larger than the other one, then it's non-directional. Okay, because I'm not specifying which one is which. Okay, so yeah, no symbols when you write out the hypotheses for the Wilcoxon Mann-Whitney test. Okay, so let's we'll try out an example. I think this is probably the best way to teach this test. Okay, and so so here, I don't really know how this works, but apparently you can record soil respiration data. So we're going to look at soil respiration, and I'm not sure how this is recorded, but we're recording how much carbon dioxide is either breathed off or absorbed by the soil or something. I'm not quite sure how it works. Okay, all right, and so so we have growth, and we have growth data and gap data. Okay, and so we looked at two areas of the forest. There's one area where there was lots of growth. There's this excellent video. Every time I think of soil respiration or just like the forest, excellent video with Richard Feynman. He's like this famous physicist, and he talks about how trees grow. And where do trees get the matter to produce their leaves and stuff? Do you guys know?
Carbon dioxide in the air.
Yeah, they produce, they breathe in the carbon dioxide from the air, and from photosynthesis, they release the oxygen and they keep the carbon to make their leaves. So it's not like they use water from the ground, but the most of the growth happens in the air and things like that. And it uses the energy of the sun to create those bonds, and then when you cut down a tree and you burn it, it's basically releasing the energy that it had absorbed from the sun. Anyway, okay. I always thought it was kind of neat.
I saw that video, and something else. Another thing interesting to think about is if it got the mass from the soil, there'd be a tree-sized hole in the ground where the tree is.
Right, right. So it's anyway, okay. So this is our data. We have soil respiration values from an area in the forest where there is great growth, soil respiration values from an area in the forest where there is a gap. Okay, and so here our null hypothesis would be that the distribution of the populations, okay? So the populations corresponding to the growth data and the gap data have the same distribution. Okay, and then our alternative, we'll use a directional one. We're going to say that there's more, that the growth values are larger than the gap values. Okay, so we'll say the population for the growth data tends to produce larger values than the population for the gap data. Okay. Is that okay for the statement of a hypothesis? Okay. All right, and we can see if we that this would be the correct situation to use the Wilcoxon Mann-Whitney test, because if we look at the growth data, we see, you know, some very large values to the point where, you know, it's kind of like, you know, what the outliers are, but we've got some really large values in comparison to kind of, you know, the gap data values. And so this is kind of an indication that, you know, these growth numbers, whatever parent population we have here, it's probably not going to be the normal distribution, okay? And then we only have, you know, 7 or 8 values, so it's not big enough for us to say, it's big enough for the central limit theorem to work. These are, we have, you know, relatively small samples. Okay, so so the way this is going to work, so our first step will be to arrange the values in columns from least to greatest. Okay, and then after we do that, we are going to count the number of values, or number of values in the other column smaller than a particular value. It sounds funny to write, but it'll all make sense when we try this out. Okay, so kind of in the center here, I'm going to make my 2 columns of data. So I've got growth, and I've got the gap values, okay? And putting these in order from least to greatest, I'm going to have 17, 20, 22, 64, 170, 190, and 315. And then on the other side, I will have 6, 13, 14, 15, 16, 18, 22, and 29, okay? And so, so for each value over here, I'm going to look in the other column and count how many values are smaller than this one. So I start at 17 and I go, in the other column I've got, you know, 1, 2, 3, 4, 5. 5 values, so 16, 15, 14, 13, and 6. 1, 2, 3, 4, 5. 5 values are smaller than 17. Okay? And then I go to the 20 and I say, how many values over here are smaller than 20? I've got 6 values. Okay? At 22, I have 6 values that are smaller and 1 that's a tie. So ties are worth 0.5 each. Okay, so here I have a 22, so I have a you know, 6 values that are smaller, 1 that's tied, so I would have a 6.5. Okay, if I had 2 values of 22 in the gap column, they would each be worth half a point, and so I would write a 7 here. Okay. Okay, and at 64, all 8 values in the gap column are smaller. Okay. And then, and you know, at 170, all 8 values, and at 190 and at 315, all 8 values are smaller. Okay, so each of these get the value of 8 assigned to them. Okay, over here I do the same thing, and I say how many values in the other column are smaller than 6, and we say 0, 0, 0, 0. So all of these 0 values in the other column are smaller. At 18, I have 1 value that's smaller in the other column. At 22, I have 2 values that are smaller and a tie at 2.5. Okay, 2.5. And at 29, I have 3 values that are smaller. Okay, so far so good? Okay, and then what I do is I just add these columns up. Okay, and so if I add this column up, I get 6.5. And if I add this column up, I get 49.5. So step 3 would be add up the columns. Okay, and then and your test statistic is the larger of these 2 values. And test statistic, for whatever reason we use the letter U, is the larger value. Okay, so in our case, our test statistic U is 49.5. Okay, and at this point, we're going to go to a reference table specifically for the Wilcoxon Mann-Whitney test, and we're going to look up this test statistic U to get a p-value. Okay. I should note that because we have a directional alternative, we should check to make sure that directionality is met. And the way we do that is, so here it says the population for the growth data tends to produce larger values than the population for the gap data. Well, that means the test statistic that we use, we look at this sum for the growth and the sum for the gap, and we see that indeed this number is larger than this number, and so so that matches our directionality. Okay, if this had said the gap data tends to produce larger values than the growth data, we would see 6.5 is smaller than 49.5, and we would say the directionality is not met. Okay, but here directionality is met. Maybe I'll write that, and I'll say directionality is met because 49.5 growth is larger than the 6.5 gap value. Okay. All right. So we'll turn in your reference table. One of them should be the Wilcoxon Mann-Whitney reference table. Let me see if I can pull it up on the screen here. Maybe I don't have it here. Oh, here it is. Okay. All right, where is it? Okay. And then, so you'll see we have two columns. We have an n and we have an n prime. Okay. And so, whichever n we have in our data, we have two n's. We've got n1 is, I've got 7 data points over here, and n2, I have 8 data points. Okay. And so whichever of these n's are larger, 8 is going to be our n, so n is going to be 8, and n prime is going to be 7. Okay, so you've got two samples. Whichever sample has more values, that's going to be 8, the n, and then the sample with fewer values will be n prime. Okay, so here I'm going to go to n is equal to 8, right here, and then I'm going to go to the row where n prime is 7. Okay, and now I'm going to look for my my test statistic 49.5 among these bold print letters. Okay, and so what do I have? I got 49.5. We go here, and we see 49.5 is between 48 and 50. If if this one was like 23. And so I had a full number, and I would have like 50, okay? Then my corresponding tail area would be exactly 0.0093, okay? So in this case, because of the way the test works, sometimes you get the exact thing, okay? But sometimes we're in between, and so we're okay with this. It's between 48 and 50, so that means our corresponding tail area is between 0.021 and 0.0093. So, what do I have? I got 49.5 is between 48 and 50. So our tail area is between, what do I have? 0.021 and 0.0093. And then if we look at the top of our table, it says the p-values for a non-directional alternative is in italics, which is those values we used. So that's a non-directional alternative. Directional p-values are found by dividing these numbers in half. Okay, and that's what we have in our case, in our test. We have a directional alternative. So our p-value is between 0.021 divided by 2, and that's going to be 0.0105 and 0.0093 divided by 2, 0.00465. So, I think we would agree that our p-value is small, and therefore we have evidence to reject the null hypothesis, and we would come to the conclusion that the population for the growth data tends to produce larger values than the population for the gap data. Okay, so I guess maybe I'll copy this part. Oops. Excuse me. Thank you. Okay, so we would say, if let's say, if alpha is 0.05, our p-value is less than alpha. Okay, so we would say we reject the null hypothesis. We have evidence that the population for the growth data tends to produce larger values than the population for the gap data. Okay. And that is the Wilcoxon Mann-Whitney test. Okay. Again, if you were to take another class in the future, I think the test that seems to be more popular in other textbooks is the Wilcoxon rank sum test, and they both serve the same purpose. They're equivalent in their results, but when you learn how to do it, it looks different and it feels a little different, and you'll have like a separate table for that. The table for the Wilcoxon Mann-Whitney test is generated from looking at all the possible distributions of basically 2 samples of data, and basically how these values can come about, and how likely a value like 49.5 would happen from random chance. You'll notice that it's kind of like these values 170, 190, 315. I could throw in a value of 10 billion here, and the amount that it would contribute to the test statistic would be 8 in all of those cases. Okay, and so this is where the nonparametric test is useful when you have these extreme outliers. It's you don't have to worry about the original distribution, but it is also, quote, less powerful, or you're less likely to reject the null hypothesis when you need to, or when you're supposed to, because it really doesn't take into account certain magnitudes. It just kind of compares how one ranks against another, rather than you know, like if you're getting a value of 10 billion in your data, that in of itself should indicate something interesting is going on, okay, and probably requires a separate investigation. But the nonparametric tests don't really take that into account. Yes.
What exactly is growth and gap?
This is just some example that the textbook provided, which was we're going to the forest and we are measuring soil respiration, and apparently there's like a patch in the forest where there was very little growth, and we said there was a gap in the growth there, and we were looking at the soil, like maybe the soil was less fertile in that area or something. That's kind of what.
So that's specific
to this thing. Yeah, it's not. Yeah, that's just this. We could have called it just sample 1 and sample 2, or sample A and sample B. Yeah, exactly. Okay, so that is the Wilcoxon Mann-Whitney test. That is the one non-parametric test we will learn in this class. And we will carry on here, okay? I read somewhere someone compared non-parametric tests to sports, and parametric tests to business. So in a sports game, it doesn't really matter if it was a close game or if it was a complete blowout. It just goes down as a win or a loss. Okay. In business, it's a big difference if you missed your target projection by $100, or you missed your target projection by $1 million. Those are very big differences. So parametric tests, those differences count. In non-parametric tests, it's less important. So kind of anyway. Okay, so now we're going to change gears here completely, and we are going to deal with kind of hypothesis tests or statistical inference for categorical data. And we can first start off with kind of a confidence interval for the population proportion P. Okay, so and so this works if you have a dichotomous situation. Okay, so this is for and what we mean by a dichotomous situation is that really there's just one category you care about, okay, and that's the category that you've assigned for the proportion P, okay, and it's either that category, it is that category, or it's not that category, okay, so really it's just maybe only either something, either an observation is in the category, or it is not. Okay, so it could be, P could reference the proportion of candies that are red versus candies that are not red. Okay, like if we're talking about M&Ms, I know there's like whatever 6 colors, but we would have to turn it into a dichotomous situation where it's either red or it's not red, okay? Or, you know, if we're talking about something else, it's either you pick one category and you say it either is this thing or it's not that thing, okay? Either the person is over the age of 25 or the person is not over the age of 25 or something like that, okay? You just kind of split the population into those that are and those that are not, okay? And so in this case, we would have n would be our sample size, and then y will be the number of quote-unquote successes, or you know, the number of observations in said category. Okay, and so our sample proportion would be p hat. Which would just be y over n, okay? Now, again, our textbook here chooses to do something a little bit unusual. I understand why it is choosing to teach this, and it is probably a good thing that it is, but again, if you were to take another statistics class in the future, I would say our textbook is fairly unique in teaching this method as its like intro thing. It just complicates it just a tiny bit, but I would say it's and it's not like hard to learn, but I haven't seen it done in any other intro textbook. Okay, so I'm just kind of giving you a warning here. Okay, so so the sample proportion is p hat is y over n. Okay. But our textbook chooses to use what's called the Wilson adjusted proportion. Okay, so this is another person, not Wilcoxon or Mann or Whitney, but those were three people that wanted their name attached to the test, because when you come up with a new statistical methodology, you say, I'm gonna put my name on this thing, okay? Okay, so this is the Wilson adjusted proportion, and we use the symbol p squiggle or p tilde, and basically we just add on 2 to y, and we add on 4 to n. Okay, now why would we do such a thing? What this does is it's like it's fudging the numbers, okay? But it's okay that we're doing this. Yeah. So let's say you were trying to find the proportion of, I don't know, people with some rare disease, okay? And so let's say you observed, 200 people, and in that 200 people, like no one has it, okay? So I don't know, like what proportion of Americans have Zika right now or something like that, right? Okay, it's pretty rare at this point. So if we were to survey 200 random people, there's a good chance that we're going to get 0, okay? But if we were to use 0, it messes up our standard error. Like our standard error would be 0, and we would come to the conclusion that no one has Zika, which might be the case. But just because you didn't observe it in your sample doesn't mean it doesn't exist in the world, type of thing, okay? And so what this does is anytime you're at the extreme where you either have 0 of something or close to 100% of something, it basically adds in 2 to the numerator, so you no longer have 0, okay? But it also adds in 4 to the denominator. So if you had 100% before, you no longer have 100%, and over here you no longer have 0%. Okay, so it just kind of takes it away from those boundary edges, which now gives us a little bit of standard error and things like that. Okay, so it just basically helps avoid p hat equal to 0 or p hat equal to 1 situations. Okay, which would be problematic as far as our calculations go. Okay, so it's not hard to add 2 and 4 to your numbers, but yeah, as far as intro textbooks go, this is the only one I've seen teach this method. Okay. All right, and then do you guys remember what a confidence interval for mu looks like? So the confidence interval for mu, it's we're trying to create an interval of plausible values for the population mean based on your sample mean, right? And yeah, so we put y bar in the middle, and then we go plus or minus our margin of error, which is t times our standard error. Okay, same exact idea holds here. Okay, we're creating a confidence interval for the population proportion p. Okay. Right now, our current best guess for the population proportion p is going to be our Wilson adjusted proportion. So that's going to go right in the middle. Okay. And then we're going to go plus or minus our standard error, or I'm sorry, our margin of error, which is going to be a critical value z times our standard error. Okay. So it's going to be kind of z star times our standard error. Okay. So this takes on a very similar form as the confidence interval for mu, except now we have a p in here. Okay, and so as far as a 95% confidence interval goes, we're going to have p tilde plus or minus our z star is going to be 1.96, and our standard error is going to be that. Okay, and it's just it really is just a matter of plugging and chugging along here. Okay, you just you observe the number of observations over your sample size, number of successes over your sample size, and you just kind of plug it in here and you get your confidence interval. Okay, all right, and you would then come to the conclusion, and you'd say something like, I am 95% confident that the proportion of, whatever it is, proportion of people with such and such disease, or proportion of dogs that, I don't know. Okay, so I'm 95% confident that the proportion of whatever in the population is between blank, so this is kind of your low end, and blank on the high end. Okay, and then and if you remember all of the interpretations, like, should I go over confidence interval stuff? Like, if I said, so if our confidence interval ended up being between 50, I'm 95% confident that the proportion of, I don't know, blah 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 blah, whatever, proportion of people who are going to vote for such and such candidate is between 45% and 55%, okay, let's say this is my confidence interval, then we can ask questions like, do I have evidence that the proportion of people who are going to vote for whoever is not 60%? And you would say, yes, because my interval goes from 45 to 55 and 60 is outside of that, right? But then I said, do I have evidence that it's not 52%? You would say no, because it's inside the interval. Okay, so the same kind of interpretations, yes.
If you don't mind reminding us just how we get the 1.96.
Oh yeah. Okay, so this is based off of the normal distribution. I kind of skipped a lot of the theoretical part here. So the sampling distribution of p hat is can be approximated with a normal distribution in the same way that a binomial distribution can be approximated with a normal distribution, because if you well anyway.
It's analogous to the binomial.
Yeah, it's analogous to the binomial and normal. And then so if you wanted to get the middle 95% in the normal distribution, okay, if I want 95% in the middle, I would put 2.5% in this tail and 2.5% in this tail. And this would give me, if I want 2.5% in this tail, I would have negative 1.96. And if I want 2.5% in this tail, I would have z is equal to positive 1.96. Okay? And that's where we're getting it. Okay? And that's actually kind of where we're getting the +2 over the +4. It's we're just kind of rounding off 1.96 to 2, and 2 squared is 4, and that's what we're using. In this class, I'm just going to we're just going to bother with the 95% confidence interval. We're not going to bother trying to make 90% confidence intervals or whatever, as far as for P go. Okay. Well, why don't we take a break here, and then we'll come back and we'll do all the chi-squared tests.